is the third video about bifurcations, the topic of section 1.7. In this video, I'd like to focus on a harder example and how to go about thinking about that harder example, and also move into some generalities that you can say about when bifurcations occur. Here's the example we'll consider. dy dt equals negative y cubed plus alpha y minus 1. dy dt equals negative y cubed plus alpha y minus 1. Alpha is now my parameter in this video. In the first video it was mu, in the second video I called it a, and in this video I decided to call it alpha. You can call it anything you want, again, as long as you don't call it the same names as the independent and dependent variables. What's different this time? Well, it's cubic. The first two examples in the first two videos were both quadratics. We could use the quadratic formula. Cubics, well, there are very complicated recipes for solving cubic equations which would allow us to find the equilibrium points for this differential equation. However, those recipes are very complicated, definitely something that I'm not going to get into in this course. So what do? Can we find the bifurcation points, the values of the parameter alpha? Alpha is the parameter here. The values of alpha where a big change occurs, or will we not be able to? Let's see what we can do. First, let's think about it qualitatively. Let's try to imagine what's going to happen before we actually try to do some calculations. That's a very good approach. If you can think qualitatively, thinking about graphs, and try to figure out what's going to happen just based on graphs, that gives you insight into what you should expect when you work with your equations, when you do some quantitative work. As we've seen, the right-hand side as a function of y is often quite important. It's very important for these autonomous differential equations to think about graphing the right-hand side as a function of y, where you put y on the horizontal axis. Then when you go to the phase lines or graphing solution curves in the ty plane, you put y on the vertical axis. And it's this flexibility that you need to have to be able to handle problems like this. A little extra bit of notation. I'm going to put a subscript for that function. I'm going to put the parameter name, in this case alpha, as my subscript of this function. Emphasizing that I've got a family of differential equations, a family of functions, one differential equation and one function for each value of the parameter alpha. We need to graph that. Now, you certainly can use some techniques from calculus that you have learned, for example, taking the derivative and finding critical points, to figure out what the graph of this is going to look like. But let's see how far we can get without calculus. That's always a good exercise. One thing that we can see right away is that the vertical intercept for this function f sub alpha of y is always going to equal -1, no matter what alpha is. So I always have a vertical axis intercept at -1. As I told you in the previous video, the coefficient of the constant term, in this case alpha, is going to be the derivative at y equals 0. It's going to be the slope of the graph when y is 0. So that's going to change as alpha changes. If alpha starts out negative, so I'll label this graph with alpha equaling negative, the vertical, be careful, the vertical axis here is not being labeled with the letter alpha. You would want to label the horizontal axis with a y. The vertical axis could be labeled with dy dt if you like, to keep track of the fact that the vertical axis is measuring the derivative. You could also just label it with a y prime. alpha is less than 0, the slope at y equals 0 is going to be negative. So my function is going to be going down at y equals 0 like that. I also have knowledge that the fact that I have a cubic tells me what kind of shape is possible, and also the fact that the leading coefficient of the cube term is negative tells me that about the asymptotic behavior of the function. In particular, when y is going off to minus infinity, when you're going off to the left, the graph goes up. Or you might say it comes down from plus infinity when y gets bigger away from minus infinity. And when y is big and positive, because that leading coefficient is negative, the end behavior, the asymptotic behavior, is downward over there too. The slope is negative over there. What's going to happen in between? Well, here's one thing you could definitely say. You're definitely going to have at least one y-intercept, one horizontal axis intercept, right around here somewhere. Because the graph is up here when y is large and negative, and it's at -1 when y is 0. It's got to cross someplace. This is a continuous function. There's something called the intermediate value theorem that would guarantee that that graph crosses the horizontal axis at least once. Will it cross more than once? Well, it could conceivably cross up to 3 times because we have a cubic. It's going to turn out that with a negative value of alpha, that it will only cross once. Let's get rid of this part here. It will only cross once. And in fact, will have no critical points. How could we verify that it has no critical points? Maybe we should do some actual calculations now. Go back to this right-hand side and differentiate it. F sub alpha prime of y is going to be -3y squared plus alpha. -3y squared plus alpha. If alpha is negative, that's never going to equal 0 for real values of y. It will always be, this derivative will always be negative, meaning the slope of the original function will always be negative. It will always be decreasing. When alpha equals 0, then the slope at 0 is 0, at y equals 0 is 0. And in fact, that point right there will be a critical point. If you think about the derivative here, if you imagine alpha is 0, you'll get -3y squared for the derivative. That will equal 0 when y is 0. But it's negative otherwise. You've got a critical point that's neither a local min or a local max at this point. It is an inflection point. In fact, if you took the second derivative, you get -6y. If you plug in y equals 0, you'd see that that gives you a second derivative equal to 0, and in fact it changes sign. So that is an inflection point, but it's not a local max or a local min. As far as the differential equations go, if you think about it, the phase line is going to look basically the same in both of these cases. What about if alpha is just barely positive? I'm labeling this positive, but let's imagine that it's just barely positive. Then the slope at -1 is going to be barely positive. And if alpha is just barely positive, it's not going to be a big enough slope for this to go back above the horizontal axis. The -y cubed term is going to dominate pretty quickly enough that it doesn't make it back up to the y-axis over there. And so even though now we've got, I guess there would be a critical point to the left of y equals 0 here, even though we've got a cubic that has 2 critical points now, one a local max and one a local min, because we aren't crossing the horizontal axis here yet, a bifurcation still has not occurred. The phase line is going to look basically the same. It's only when we get to a larger value of alpha, I'm going to call it alpha star, somewhat larger than 0, I'm not sure how much yet, then a bifurcation will occur. Just drawing it very quickly. The graph will just touch the horizontal axis at one point. And then once you're past alpha star, once alpha is bigger than that, once again, just drawing a very quick sketch, now you're going to have 3 horizontal intercepts. A bifurcation has occurred. Now we've got 3 equilibrium solutions, 3 equilibrium points on the phase line. So this is a very good thing to think about when you encounter problems that are more difficult like this. Or in this example, we can't use the quadratic formula to predict what's going to happen. We can gain extra confirmation from the computer. Let's use Mathematica first. I showed you in the last video how to use manipulate. I'll use that again. So my function is negative y cubed plus alpha times y. I'll just type it in as an a. Keep it simple here. Minus 1. I'm plotting that with y being on the horizontal axis. Keep my plot range constant. And let a, or alpha, if you like, vary. I'll try negative 3 to positive 3 and see what happens. Is that showing up pretty well? Oh, got to do my plot style thick. There we go. So there, a is negative 3. Now I run the animation. You can see what's happening. It looks like we get a bifurcation occurring if you look at the number up here at about, close to 2. Close to alpha equals positive 2. Somewhere around there. I can't quite catch it. Maybe if we pause this, we can run the slider ourselves. Looks like it's going to be a little bit before 2, like about 1.9 or so. If you look at the number, the bifurcation occurs. We change, a big change from 1 equilibrium point up to 3 equilibrium points once you get past alpha star. Technically, at alpha equals alpha star, you would have 2. Can we actually figure out what alpha is? In this case, yes, we can. But how? We don't have the quadratic formula. Let's think about this. What kind of thing is happening at this point? I might call that y star at that value of alpha. Well, one thing that's happening, and this happened with the quadratic examples too, is that you have a root for the right-hand side at that value of y, which occurs at that value of alpha. So the function equals 0. Also, another thing that happens is that the derivative of the function at that point is 0. It is a critical point when it crosses there. That really gives us a system of 2 equations that we need to solve. Again, f sub alpha of y is negative y cubed plus alpha y minus 1. Its derivative, f sub alpha prime of y, is negative 3y squared plus alpha, We want to find a value of alpha and a value of y that make both of these equal to 0 simultaneously. It's really a system of two equations and two unknowns. Set these both equal to 0 and solve for alpha and y. Can we do that? Yes, you can. One thing you can do is you could take this equation and solve it for alpha in terms of y. If that equation is true, then alpha will equal 3y squared. Then that can be substituted into the first equation in place of alpha. So if we do that, substitute, we've got negative y cubed plus alpha y, that'll be 3y cubed, 3y squared times y, minus 1 equals 0. Still a cubic equation, but this one can be solved. If we simplify it, 2y cubed equals 1, or y cubed equals 1/2, that has one real solution. See it okay? That has one real solution. That's got y equals 1 over the cube root of 2 as a solution, or if you prefer, 2 to the negative 1/3 power. You can then use that to figure out what alpha is. We found the location of the equilibrium point when the bifurcation occurs. What about the bifurcation point itself? What about the value of alpha, alpha star? That is where the bifurcation occurs. Now I'll just go back up here and substitute what you found in for y. To get alpha is 3 over cube root of 2, or if you prefer, 3 times 2 to the negative 1/3. You might want to get your calculator and approximate this. 3 divided by 2 to the 1/3 power. And I'm not getting the correct thing. I guess this is good that I made a mistake. Let's see here. I'm getting about 2.38. Why don't we stop the video for the moment, and I'll come back after I figured out the mistake. I found my mistake. Hopefully you took the time to see if you could find my mistake. I forgot to square y. Alpha is 3y squared. I should have squared this 1 over cube root of 2. What you end up getting is 3 over 2 to the 2/3, or if you prefer, 3 times 2 to the negative 2/3. That's the bifurcation point. That's alpha star, and it is about 1.89. That's the approximate bifurcation point, is 1.89. This quantity, 3 times 2 to the negative 2/3 power, is this number alpha star. Okay? So that's the bifurcation point. That's where it occurs. And this is the y, the equilibrium point for y at that bifurcation point. You should draw a bifurcation diagram. Let's do that real quickly. Okay, again, the parameter goes on the horizontal axis this time. That's alpha in this case. Y goes on the vertical axis. You're making a bunch of phase lines going up and down for different values of alpha. When alpha was negative, Well, careful there. Don't forget, there was one equilibrium point that's always back over here for negative values of y. That one's always there. It doesn't always stay in the same spot, but it is always there. I guess as y increases, it looks like that equilibrium point decreases. It's negative, it's down here. Excuse me, as alpha increases, that one decreases. It goes further away from y equals 0. When y is less than that, dy dt was positive, and when y was greater than that, dy dt was negative. Thinking about the graph of the function on the right-hand side. So we get a bunch of pictures like this. This point just heads off down this way. Let's pretend alpha star is right about there. That's again about 1.89. That's the place where a bifurcation occurs. It occurs at y, again, is 2 to the negative 1/3 power, up here somewhere. At that spot, you get just that one equilibrium point up here. You still have the one down here. And you can check, based on the sign of the right-hand side, that you're going to get those kind of arrows. And once those points spread out, I guess that point will never quite reach the alpha axis there. It never quite reaches y equals 0. You see that in between those two equilibria, you've got solutions going upwards, increasing. And you can check that out by looking at the right-hand side, the graph. These are how the arrows should go. So bifurcation occurs right here. There's some curve, I don't know what it is exactly, down here that's keeping track of the far left equilibrium point, the negative one, that's there no matter what alpha is. Let's confirm this with the CD-ROM real quickly. In fact, I picked this equation so that it was one of the choices. Can you zoom in on that? Zoom in on that as well as you can. Look in the bottom right corner, and you've got these different options for the equations. I picked the one that's the second from the bottom. It's labeled r plus ay minus y cubed. I picked r to be negative 1. You really, in this thing, you actually have two parameters, an a and an r. But I set the r to be negative 1. And what you're seeing up here is the bifurcation diagram. At least in a certain window. If I change the slider for a, we see that when a is negative or alpha is negative, you get the picture that I showed you. Here is alpha 0, and here right about there is real close to your bifurcation value of alpha. Notice down here it says a is 1.90 down here. And if you look up here, you can see there are two equilibria that have bifurcated from nothing. And you move alpha bigger, and those two equilibria move away from each other. You can see the phase line here for a value of alpha bigger than alpha star. And you should also think about the slope field over to the left here. Think about how it's related to the actual solutions of the differential equations. In this case, we actually have three equilibrium solutions. There's one way down here, that's the negative one right about there, and one up here. And this one's called stable, the solutions approach. That one as t goes to infinity. This red one's unstable, they go away from that one as t goes to infinity. And the green one down here is stable. Solution curves that are nearby go towards it as t goes to infinity. So you always want to keep in mind that this is still all related to solutions of differential equations. The phase lines are just nice ways of thinking about it. Last thing I want to show you here is a little animation that's kind of fun. Bifurcation problems can get very, very complicated. Let's imagine one that might be very complicated. Imagine dy dt equals, say, 2 times sine of a times cosine of sine of a minus 1 times y plus 3 times sine of a. Imagine that's your equation. Okay, so dy dt equals that thing. Y is the variable, a is a parameter. If you try plotting this over the usual kind of range, as a changes, I'm going to plot it. Negative 5 to 5, I'll try. Plot style, thick, and let a vary. I'll start at 0 and go up to, maybe it's something like 4 pi. Let's see what happens here. Okay, there's how the right-hand side of the differential equation is changing as a changes. Imagine trying to find the bifurcation points of that, okay? What values of a does it cross through the horizontal axis? It would be pretty hard to find. You can also draw a bifurcation diagram of this. Although what I'm going to show you does not draw the arrows. Using something called contour plot. Oh, we're not seeing it very well. Let's see. Okay, well, this is not giving me a very good picture. You just see some vertical lines there. Maybe what I'll do is I'll maybe modify this example somewhat and save it, and you can look at it. I'm not sure what's going on here, that it's not coming out nicely. Maybe I'll just try modifying it a bit. See if anything changes. Well, I guess it didn't. And I'll save that file for you, and you can look at it. I'm not sure what's wrong, but you can get some pretty wild-looking bifurcation diagrams too, and I'm sure you would with this. That's the end.